Hi, for those of you who already joined, we'll be waiting for another couple of minutes and then go ahead and get started. All right, let's go ahead and get started. Good afternoon, everyone, or good morning, depending on where you are. My name is Julia Matevosyan. I'm Associate Director and Chief Engineer at Energy Systems Integration Group, or ESIG, and I would like to welcome you all to our ESIG webinar. For those of you not familiar with ESIG, we are a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of clean energy and energy systems integration decisions. We do this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resource materials. For those of you who are members, thank you for your support. It makes possible these webinars and other work that we do. Using this opportunity, I would also like to invite you all to our upcoming ESIG Spring Technical Workshop in Austin, in Texas, the week of March 17th. As always, the workshop will host a mix of technical content with additional focus on large loads integration. And in fact, on Thursday of the workshop, we'll also have a large loads workshop. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on the ESIG website at www.esig.energy or find us on LinkedIn, YouTube, Facebook, and Twitter. Okay, just a few logistical matters. First of all, participants' lines will be muted for the duration of the webinar to avoid unnecessary distraction. For Q&A, please use Slido platform at slido.com, enter ESIG4 as the event code. You will not be able to ask your questions through WebEx, so please use slido.com. The instructions are also currently available at the bottom of the screen. You will see a thumbs up button next to questions to allow you to cast your vote, and it helps us prioritize the questions that were submitted. We plan to save 10-15 minutes for Q&A at the end, and then we'll wrap up at the top of the hour. An email link will go out once the video have been posted. We also plan to provide short responses to all unanswered questions after the webinar, so please don't be afraid to ask your question on Slido. All right, so introducing today's topic and speakers, grid forming inverter technology continues to be focal point of discussion and potential key ingredient for energy transition. Grid forming is particularly attractive in battery energy storage systems for multiple reasons and is commercially available in batteries today. However, a small number of grid forming projects exist in the US, and this may be due to gaps in the pathways to widespread adoption for grid forming technology, especially in batteries. Limited understanding of the models and studies that provide technology that proof technology brings value and supports reliability in large interconnected bulk power systems is an immediate challenge. So to address this challenge, we had ESIG project team that collaborated with American Transmission Company, ATC, and they embarked on a study of grid forming performance in realistic network. The primary objective of the work was to test whether grid forming battery energy storage is a do no harm solution, how significant growth of grid forming batteries would affect system performance, how grid forming batteries operate in weak grid situations as well as strong grids, and whether grid forming can serve as a viable solution to defer other longer lead time solution options. So this webinar will cover work done in the study, key findings and recommendations moving forward in this area. So today, the webinar will be presented by the leadership team of the ESIG project team, and it's Ryan, Quint, and Farhad Yahyaie from Elevate Energy Consulting, Andrew Isaacs and Lukas Unruh from Electranix, and they will be presenting the results and key findings of the study. I believe these people actually don't need long introductions. I'm sure many of you know them, but if you're interested to learn more about them, the short bios are available on the webinar page. So just a short reminder again, use Slido at slido.com with event code ESIG4 to ask your questions. And without any further ado, let's go ahead and get started. I now turn it over to you.
Great, thanks, Julia, and thanks everyone for joining us. We're really excited to be here sharing the work we've been doing with under the ESIG project team and for this study and partners with ATC and the OEM. So this is kind of a culmination of the work we've done and kind of the core deliverable here. So just wanted to share our learnings. So just to kind of start, just wanted to acknowledge the folks at Electranix, Andrew and Lukas and the team. They've done a tremendous job. It's been a really insightful project, learning all kinds of new things about grid forming technology on real systems. It's been a fun project for sure. Also wanted to acknowledge the project team. We had a really good team. We had monthly meetings where we brought in report outs of the modeling and the study work we did. We had some technical discussions and lots of presentations from real world grid forming experience from industry experts really around the world. So as Julie mentioned, some parts of the world are ahead in some regards, have deployed grid forming, and so we learned from that experience. We also learned from entities that are developing requirements presently and the findings and learnings and the challenges they faced. We had really good coordination calls with the ATC and a great project partner there with really good models, and Lukas will talk more about that later. And we're going to be having a couple more deliverables coming. We're working on this presentation will get posted online. We've also got a high-level brief for decision makers, policymakers, and regulators that cover the high-level takeaways from the study work we did, and we'll be doing concerted outreach to some of those key stakeholders to make sure the key messages get across. Really good meetings, the lineups there. I won't go through each one of these, but I did want to just highlight, if you go to the ESIG webpage, go to working groups, go down in the tab to reliability working group. Under reliability working group, scroll down, you'll see benefits of GFM BESS project team, and you'll see all those presentations listed there. When the materials come out, these links are at the bottom of these slides as well, but just wanted to make sure everyone knew where to get the material. Why we're focusing specifically on batteries, and I think this version of this slide has been presented in many different forms and capacities, but really it's readily available. There's little mechanical difficulties and challenges with batteries as compared to, say, wind. It's really a focused software update. There can be some hardware considerations that need to be made, systems integration, SCADA integration, those types of things. But by and large, it's much more focused on software. It's a ready technology. Multiple OEMs have a grid forming product that has been deployed around the world. And relative to the other technologies, at least, it's a relatively low solution option compared to grid forming in wind, for example, or even solar. So that really draws our attention into batteries. And so the focus of the work and the project here was really focused on grid forming batteries specifically. And we'll talk more about that as we get into it. Just wanted to highlight, this is kind of a moving target, but a growing list of some grid forming projects in the United States. We've got the Mackinac HVDC circuit, which is actually up in the ATC footprint. It's kind of the classical HVDC, but wasn't called, or classical grid forming, but isn't called grid forming. When you go back and you look at the literature and the papers that were written about a decade ago, there's the Cape Cod grid forming battery project, a small or a skinny radial connection to the rest of the bulk power system, connecting a battery out there for resilience and stability purposes. And more recently, the South Fork offshore wind project has a GFM StatCom as well. So definitely growing experience with the technology in the U.S. But as Julia alluded to, we're starting to pose this question: why aren't we seeing more? If it's a low cost, high value product, where are we struggling to see a broader, widespread adoption of the technology? And so we put this together really just to kind of go through the various categories of, the process to go from learning about the technology to deploying it out there kind of more in mass, right? So we have a relatively good understanding of the technology. It's a ready technology. It's commercially available. We are, I think, struggling a bit on the models, understanding the models, trusting the models, and then putting those models in real world systems and seeing what the benefits or the challenges would be in an actual system with those resources deployed. We've got some pilots around the world, but not a lot here in the US. And so there's always that utility environment trust of, I don't know about being version number 0.1. Let's see it put into practice. And so I think we need more pilots. And then kind of longer term is regulatory and or market side. And that's a discussion in and of itself that's really, we're not focusing on today. But in the long term, do we need any type of standardization on this? Like I mentioned, there's been all kinds of work done around the world. Lots of great materials out there, and ESIG's been doing a really good job of housing references and links to all of these references as well. So if you're interested, make sure to go take a look at the ESIG page on grid forming. What we really wanted to talk about today was really three categories of topics. The first one is through this project, we took the grid forming models we gathered from the OEMs. We've gathered grid forming and grid following models from actual GFM BESS manufacturers. And it was really instrumental to have them involved in the project. We ran those models through the NERC functional specifications and test procedures that were put out about a year and a half ago. We then sort of rigor tested grid forming batteries and grid following batteries in a microcosm test system to just kind of better understand the characteristics of them. And then we deployed a bunch of these grid forming batteries in a real world system, the ATC system, to explore, well, what happens when we actually try to run planning studies with these models. We're not trying to plan the grid, but we're trying to use a real world test system to better understand those benefits. In essence, it all boils down to we're trying to see, our hypothesis was grid forming batteries are a do no harm solution, and we're trying to put that to the test. Trying to explore, are they interoperable? If we start mixing grid forming and grid following batteries with each other, does that cause any problems? What about different OEMs and their control strategies? What about grid forming in weak systems? What about grid forming in strong systems? What happens if we see a significant growth of grid forming batteries in a pocket? Can grid forming help defer other solution options or help bridge to longer term solution options like transmission infrastructure development? What benefits can we get out of these? And then as we went through the process, we collaborated with the OEMs, and anything we came across, we tried to provide feedback to them along the way. So with that, I'll hand it over to Farhad to talk about the modeling.
Thanks, Ryan. So the first part that I'm going to focus on is this NERC guideline, the white paper on the GFM BESS specification. As Ryan mentioned, NERC published that in September 2023. Basically sets sort of requirements on the GFM BESS. So the goal, I guess Ryan shared it already, is to provide some feedback to the OEMs and share the overall findings and conclusions in a generalized manner. So next slide, please. So the test system that is used in this white paper is pretty simple. It's shown in this diagram. It comprises of a BESS project rated, let's say, 100 megawatt, and a duplicate BESS project using the same model, but rated at half the capacity, 50 megawatt, and a load that is equal to 100 megawatt, and a synchronous generator and an infinite bus system that is about 300 MVA rating. In all the tests, the synchronous generator will trip after the initialization of the case and the behavior of the BESS GFM and GFL models will be evaluated. The initial condition of the three tests that are proposed are different. However, the first case uses both a project and a duplicate project as initially discharging, and after the synchronous machine trips, they will discharge at a higher level. In test 2, they're both initially charging and then end up at a discharging after the tripping of the synchronous machine. And in test 3, one of them is actually at maximum power. So once the synchronous machine trips, we are expecting the output of that unit not to change, and the other unit has to pick up the load. So I guess here is a summary of the test results on a high level. So we tested 5 different OEMs for the sake of against confidentiality. The names are removed, and we use letters A, B, C, D, E. In general, all the GFM models provided by the OEMs passed the NERC functional specification, and all the GFL or grid following models failed the test. There were some issues with some models that we were able to resolve. Unfortunately, 2 of the OEMs, they had some issues with some of their models, and they were not able to resolve the issues. Slide. Some learnings, I guess, that throughout this process, we find some issues we shared with the OEMs, and the open communication and the help that was provided by the OEM was essential to resolve some of the issues. As an example, some of the test 3 results were kind of strange. The unit that was dispatched at the maximum changed the output slightly, either increase or decrease. And throughout working with the OEM, we were able to identify the issues with the model, and it was basically parameterization of the model, and they were able to fix that in most cases. I guess the main takeaway from this slide is the engagement with the OEMs that is very much crucial in resolving these modeling and performance issues. So we want to recognize that and thank all our partners in this project. So the next set of tests was on the Microcosm system, where the system was basically to interconnect the 4 GFM models that passed the NERC white paper requirements into a smaller test system and connect them to a programmable voltage source, so we could basically change the frequency, voltage, and phase angle of the source and apply some disturbances such as load change, faults, and investigate the interoperability of these different GFMs among themselves, dynamic performance, is there any control instability issues or any adverse interactions that can occur when we combine these different OEMs. We ran a few test scenarios. Next slide, please. So I guess this high-level summary again is in all the tests that we ran, we saw a more stable and acceptable performance from running different transitions and fault scenarios. So overall, everything looked pretty good on a high level. I just wanted to emphasize the fact that for these models that we use for this study, we try not to perform any model tuning or changing of the parameters. So the parameters of the inverters and most of the controllers are default parameters that was provided by the OEM. We changed some of the droop settings on a very high level on the plant level controller to just see an overall similar type of behavior in terms of the steady state behavior. But dynamically, all the parameters, gain controllers are the default parameters that are provided by the OEM. Next slide, please. The next set of tests in this Microcosm system was to incorporate the GFL inverters as well. So basically the same sort of test that we had previously, where only GFM models were included. Now we added all the GFLs as well. And just to make sure that we treat everybody fairly, we dropped the OEM-C from this assessment, OEM-D from this assessment, because their GFL model was not working properly. So they're seeing 3 different OEMs, both the GFM and the GFL models. Again, we ran a bunch of studies on their voltage and frequency and disturbances, load change and fault. And in all cases, there was no real negative adverse interactions that we observed during this test. So I guess the high-level conclusion is that these GFM and GFLs can operate together in a stable manner. Next slide, please. We ran a different study where the ratio of the GFM versus GFL was changed. So we in the scenario that was shown earlier, if we have 3 GFL models and we applied faults, on the top plot, you can see that the system collapses. So the GFL models are not able to sustain or preserve the system stability. Whereas once we increase the amount of GFM as we increase that number or the per unitized values, we saw more stable behavior. And those different disturbances we applied are basically, we made the system weaker, we apply a strong 3-phase to ground fault, and as you can see in the middle, with 1 GFM, the system was stable for some up to a certain threshold, and then after that it became unstable. If you increase the GFM to additionally, we're able to see a stable response throughout the whole simulation. Next slide, please. We assess also the rock-off and phase angle jump. In both cases for GFM and GFL, all the models were able to ride through a rock-off of 5 bursts per second. The only observation was that the GFM provided a more aggressive response to the change than the GFL. Next slide, please. On the phase angle jump, again, both GFM and GFL models were able to ride through a phase angle jumps of up to 180 degrees. So in this plots, different phase angle jumps are applied, 30 degrees, 45 degrees, and 60 degrees, and so on, up to 180 degrees. And again, both models were able to stably run through this phase angle jumps. If you just zoom into one of these phase angle jumps, like in this plot, you see the 30 degrees phase angle jump. There's a little bit of a distinct behavior that you may recognize from the GFM versus the GFL behavior on the top plot, which shows the active power. You can see that the response of the GFM is faster and more substantial to this phase angle jump, while within the current limit, the initial power was around 20 megawatt or 20%. And it sort of like confirms the voltage source behavior, I guess, of these machines or synchronous machine kind of type of behavior as well. Next slide, please. And then finally, I guess the test that was conducted was on the speed of the response for frequency change and voltage change. One of our dear friends suggested another sort of test during this monthly meetings that we had. So here we changed the frequency on the left. The frequency of the system was changed from 60 hertz to 59.4 hertz, and then which is around 10% or 1% frequency change. And then the one on the right, it shows the voltage change of about 2% increase. Again, as you can see on the left, the blue curves that corresponds to GFM models from the 3 OEMs, GFM-A, OEM-A, B, and C. Compared to their own GFL model, we saw a more a substantial and faster response from the GFM models versus the same OEM, the GFL model. On the right side, for the voltage, this distinction is hard to make. Next slide. I think that's probably end of my presentation. Andrew?
Yeah, I'll take over here. We're in good time. Ryan and Farhad are right on track here, so that means I can take an extra 20 minutes or so. Just joking. You want to switch to the next slide there, Ryan? So I'll just introduce you to our utility partner, ATC. So here's a little snapshot of their system where it covers. It's about a 13 gigawatt peak load system. Lots of transmission, 5 million customers. It's part of the Eastern Interconnection, actually sits in the MISO footprint, so they are within MISO's frameworks for planning. And I think one of the reasons why we really wanted to choose ATC as a utility partner is a number of people sort of on the list, and we chose them for a few reasons. One is that they have quite a deep experience with EMT modeling and analysis. So they have extensive high-quality model databases, including all of their IBRs, transmission systems, and loads, and so on. They also have experience in detailed dynamic performance studies in EMT tools for at least going back 10 years, and actually routine studies, so part of their baked-in processes for at least 5 years. And for this project, ATC agreed to actually make their EMT model databases and their PSSE planning cases and dispatches available to the study team, which was extremely valuable. It gave us a big head start, and also lends credibility to the study because the system is real. ATC also helped us to develop some interesting real-world scenarios to support this effort. So they knew where their problem spots were, and they helped us sort of zoom in on some key cases and key scenarios. Now, these scenarios were in some cases extended to some extent. Like Ryan said, we weren't trying to plan their system, but we did in some cases kind of pile on the system. So where there was a battery connecting, we would connect another battery, or we would make things, even more sort of future looking to make sure that we could really illuminate the study objectives. So we wanted to see these batteries working for better or worse. The other reason why we liked ATC as a partner on this one is because they actually have a very diverse system. They have some pockets of load which are very strong, some very weak spindly systems, and a lot of renewable interconnection in the last number of years, leading to some pockets of renewables which are extremely high penetration. So kind of a perfect test bed, if you like. Next slide, please. So I'll give you a few notes about how the model was developed. So this was performed using PSCAD, which is the tool that ATC uses. So to develop a system model, we followed essentially the process typically done in the ATC footprint, which is like this. You start with your planning cases in PSSE, so that's power flow and dynamic modeling data based on key planning years and dispatches. So this is their working planning models, okay? Same things they do in PSSE. And then we take a collection of the detailed, and these are verified IBR models, so already stress tested and accepted models, and system components, so transmission lines, loads, HVDC links if needed, and all of those things are all included into a regional database. So these are all included in libraries called substitution libraries. And then based on the scenarios that were chosen by ATC, a kept system, we call it quote unquote kept system, what's going to be included in the PSCAD model is sort of surgically chosen. So which buses are important for the dynamics of the simulation we're doing. And that would vary in size depending on the specific contingency or scenario that was being studied. So it varied between about 120, 170 buses. And then all of that data goes into the ETRAN tool, which then spits out a runnable PSCAD model, which then is basically used for processing. That PSCAD model is connected and is parallelized so that it can be run faster, and integrated also with customized plotting and scripting automation that will run through those cases in an efficient way and spit out the right quantities that we want to look at. So that's the overall process. I'm going to turn it over to Lukas to get into one of these studies.
All right, thank you, Andrew. Yeah, so I'll be walking you through two of the system studies, well, the only two system studies that we looked at here. So we focused on a strong case and a weak case. And the strong case that we looked at was specifically, we were looking not so much on the benefit side, but more looking for any potential harmful impact or interactions that might be introduced by grid forming in this system. And the region that we looked at can be characterized by a strong 345 kV network. With, if we want to quantify strong, we would say the S short circuit ratios in the region were kind of above 50. And this region featured large synchronous machines and large loads. The IBRs in this system in this model were a mix of existing and planned IBRs. And then, as Andrew mentioned, we threw a couple more sort of fictitious planned grid forming or battery plants into the system. And the battery plants that we turned into grid forming plants, these in some cases they consisted of just like a single OEM inverter model for the whole plant, and in some cases it was a mix of those three different OEMs that Farhad had mentioned before, or the presented before. Yeah, so in this strong system, the IBRs were they were mostly kind of clustered on this left side, the central left side, but there were some batteries distributed on kind of the right sides here as well. And yeah, we actually studied a few different fault scenarios, but here we weren't really necessarily looking to weaken the system so much, just to sort of run some standard planning cases. And these were studied with the batteries first as grid following, which we kind of considered the base scenario, and then we switched those out with the grid forming. We looked at charging and discharging scenarios as well. Yeah, sorry, go ahead to the next slide there. So here's just a snapshot of some of the results that we found from the strong system study. And for the strong system study, we really were not really expecting to see anything too interesting, as we were mostly looking just to make sure that there was no harm caused by adding grid forming into the system. And on the left, an example of the sort of multi-OEM plant response to a three-phase fault. You can see that the grid forming, three different grid forming OEMs here, the performances, there are slightly different, some differences in the response at the fault recovery, but generally there's no harmful interactions between the two, and they're sort of sharing proportionally before and after. So that was a good sign for us. And on the right is kind of what I would pull out as probably the least damped grid forming response that we saw in this strong system study. And here you can see on the bottom plot some oscillations in Q that are damped in about 4 seconds. So relatively quickly damped over there. And yeah, so in this strong system, we kind of were able to show that grid forming BESS didn't do any harm to this strong system. We showed that multiple GFM batteries from different OEMs were able to operate reliably together. There was no unexpected interactions that we saw, and we identified possible issues integrating GFM into the strong system. In this case, we didn't actually see any in the study. So yeah, we'll move on to the weak system here, which is a little bit more interesting. Here we're specifically looking to see what benefits the grid forming BESS could offer in this weak system. So yeah, if we can talk a little bit about the specifics of the test system here. This was a weaker part of the ATC region with limited connections to the external strong transmission system. And we kind of have two main sort of corridors here on the left and the right. The left is just a single sort of POI, essentially, with a few different plants connecting to it. And on the right, we have a string of 3 POIs with plants connecting along that path. And then, yeah, we were specifically looking for faults that would sort of take some of these IBRs and remove the strong connections and have them feed potentially into this this weak sub-transmission network that's in the middle. And yeah, so this is a fairly IBR saturated region. It was yeah, you know, if once we take out some of these lines or WSCRs or SERs, they drop below 2 relatively quickly. And similar to the strong system case, we had our baseline scenario, which consisted of the batteries as grid following. And then we substituted those out for grid forming batteries. And for those grid forming batteries, we used a similar modeling approach. Some of them were just a single OEM, some of them were a mix. And it's important to note that we didn't change any of the settings for this grid forming batteries. So they weren't necessarily tuned specifically for this weak system. They were the same settings as in the strong system. And what we were trying to show, or we're trying to investigate, is do we improve the local stability of this network with GFM? Can we integrate more IBRs into the system? And can we avoid operational curtailment for certain contingencies? Next slide, please. So yeah, I'll walk through a few of the specific faults that we looked at. This one here is a fault on sort of that left corridor that removes one of the connections to the strong system for that 350 megawatt PV and 75 megawatt BESS plant there. And this one for this, so this is just an N-1, and when that 75 megawatt BESS was in grid following mode, we had the instability that's visible on the left here. So the plants can't recover. Eventually they do sort of stabilize, the voltage is low and there's big oscillation, so that's a clear fail. And then on the right, when we take that, when we take the, we changed all the batteries in the system to grid forming, but specifically really just that 75 megawatt would have been the one that made the big difference here to stabilize this case. So this is an example of where changing that plant from grid following to grid forming would avoid other need for other mitigation like transmission or synchronous condensers at that location. This next one here that we're looking at is also a N-1 fault. And this one is on the sort of that right corridor, and we're removing one of the strong connection points from that cluster. In this scenario, the system strength is a little bit hard to quantify because of the sort of distributed nature of those IBRs, but we would, using a simple WSCR, we would say it's below 1.6. The grid following, when the batteries were modeled as grid following, we had the response that's on the left here. So we would kind of say this is a marginally passing case, or could be a fail depending on the criteria that's being applied. So kind of a pretty large voltage transient at fault clearing, and then pretty heavy oscillations for about a second before things stabilize. And when we take those batteries model them as grid forming, we actually get a stable result for the N- for the sort of the base scenario. And then to sort of quantify the benefit here, we actually added an additional sort of 125 megawatts of PV into this, of grid following PV into this corridor, and we found that was stable. So this is an example where we sort of unlocked more capacity, more grid capacity for IBRs along this corridor. And then the last scenario I'll point out here is this is an N-1 fault, where we basically removed both connections from that corridor on the right and left all of the IBR generation there operating into that weak sub-transmission network. And this scenario was unstable for grid following and for grid forming when all the devices were dispatched to PMAX. So we basically just tried to see, what kind of a difference in curtailment would be needed for this sort of scenario with grid following to versus grid forming. And yeah, it was quite a big difference. So with grid following, we had to reduce the generation all the way down to reduce it by 250 megawatts, which didn't really leave a whole lot left here. Whereas with grid forming, we only had to reduce down to 50 megawatts, reduce 50 megawatts by 50 megawatts. Next slide, Ryan. And here's just a plot showing the results of the system with the different curtailment levels. So yeah, we kind of met our objectives here for the weak system as well. Grid forming BESS as a do no harm solution. Again, we just saw really a lot of benefit to using grid forming technology in this weak system. And we showed that multiple GFM BESS with different OEMs were reliable, same as in the strong system. And we did show that we were able to unlock some grid stabilizing benefits in this system by adopting GFM BESS in this network. And those were reduced need for stability-driven network upgrades and reduced curtailment for the N-1 condition. And we increased the IBR hosting capacity as well. Next slide. Okay, that's it for me. Go ahead, Ryan.
Yeah, thank you, Lukas. Yeah, thank you, Andrew and Farhad. Yeah, so if you're still on the call and you're not a studies engineer, I think we all commend you because that was a little bit dense, but that was kind of the point, right? Is that we wanted to take these, as we talked about in the ESIG project team meetings, we wanted to take real world models from real world OEMs and put them in a real world system with real world contingencies and see what would the expected performance be of these different resources, right? That whole concept of do no harm. We wanted to sort of hypothesize and test that fairly rigorously. There's a tremendous value. There's a lot of value in running exploratory studies, research projects, exploring what the next, control topology could be for grid farming, etc. But I think a missing link has been, let's see what's actually out there in terms of real product on the real system, right? So that was really the focal point of the modeling and the study work. And we really tried to put together a set of findings and recommendations, and we thought the best thing to do was just to talk through what, as Lukas just kind of elaborated on, how did our hypothesis play out, right? And our hypothesis played out exactly how we sort of thought it would, mostly. And we kept joking in the project team meetings that this is a rather boring study, right? Because everything was really stable, which was what we hypothesized to see, right? So if we asked ourselves we are not trying to expand this to every, nook and cranny of the bulk power system around the world, but on a sort of a standard Eastern interconnection grid with a diverse topology and resource mix, what we saw was that when we added in GFM batteries, not even just a little bit, but actually a lot of it, it was a rather do no harm solution for us, right? We didn't see any abnormal instability concerns. We didn't see any anomalous interactions or oscillations between devices or within plants. We put the NERC tests to the test. Number of us on the call here were involved in crafting those tests. So we genuinely, I think we're curious, do they hold up, right? And the answer was they did, right? So Farhad's graphic there, table there, showed all the grid followings failed and all the grid formings passed. That doesn't mean one's better than the other. That just means the test works as designed for the different commercial products that are out there, right? So that was just sort of a thumbs up in that regard. That tests like that can be useful for differentiating the types of grid forming, grid stabilizing attributes that we're looking for. We started, as Lukas talked about, we started piling on batteries into the networks, and we saw more stable results, not more reliability challenges. So we didn't see any reason why growth of grid forming batteries in either of those situations would cause significant reliability challenges. Every resource that's connecting to the grid must be assessed, studied, modeled, and studied to make sure that it remains reliable. But there were nothing unique about the implementation of grid forming that caused a bunch of anomalous reliability challenges. We sort of knew, because we see it around the world, that grid forming batteries can provide stability benefits in weaker grids, and we saw that pretty prominently here, even in the sort of smaller pocketed IBR system of focus, right? More more hosting capacity, less curtailment, better performance overall. Those are all really positive things that can unlock more resources connecting to the system. It worked in the strong grid, and like Farhad and Lukas both hinted at, we didn't do any magic tuning of these models. We took them off the shelf as provided. We plugged them into these systems, and they worked really well, right? So we saw a couple swings, machine-like swings from a couple plants, but overall, that was a pretty saturated system of grid forming technology, both interplant and intraplant, right? So overall, and Farhad tested it in the microcosm system, and then we tested it in the real world, that as you sort of increase that that ratio of grid forming to grid following, you see more prominent value in the weak grid pockets, and then you don't see any negative or adverse impacts in the strong grid pockets necessarily. And so when you sort of extrapolate that, we all hinted at, we didn't run network studies to try to plan the system. So we didn't look at building in a synchronous condenser or transmission infrastructure. That wasn't the purpose of the study, but it definitely could help us bridge to some of those longer term solutions and or more costly solutions, right? So could serve both of those purposes. When we try to think about, okay, what are our recommendations here, at least? What we thought was, first and foremost, I think, is, gathering these models, developing the models, testing the models, and then conducting system studies, right? Quantify those benefits on your local system. That's a great place to start. What happens if I start putting GFM in areas that could otherwise run into stability challenges under N-1 or N-1-1, or even under extreme conditions, right? That helps you sort of understand and visualize and feel the value that it could bring. And it becomes a really useful tool in your toolbox to deploy in areas like weak grids or near series capacitors where you run into subsynchronous oscillation issues. But it even can help with and or support strong grids, right? Which leads to maybe wider spread adoption than just niche weak grid conditions, right? Can help maximize project value, right? From a developer's perspective. It could lower the risk of running into stability implications for new IBR interconnections. It could increase the amount of IBR interconnections within a specific pocket. Could reduce curtailment under N-1-1 operational conditions, and could potentially minimize the required network upgrades. So it could be used as a tool for sensitivities. If the network upgrade requires a synchronous condenser, one could ask, well, can we solve that problem with a battery, with a grid forming battery, right? Next recommendation we mentioned earlier, but pilot, right? Try, think about deploying this and gaining that operational experience on the system early before that future with a lot more challenges with a very saturated grid following system could arise, right? Can we get out in front of that likely future by deploying some of these resources early and learning from that? If you're going through any of that in terms of actual deployment of the technology, you really need to have these technical requirements or functional specifications, whatever you want to call that, and you can integrate those into your facility interconnection requirements, market rules, or wherever you house your technical requirements for newly interconnecting resources, and maybe even include it, from a state regulatory perspective. Think about including it in RFPs for new resources, given that it's a very low cost solution for grid stability problems, right? Having the capability of the resource to be able to provide it, or having the operational requirement to have the thing enabled in that mode, right? So in a nutshell, our key takeaway was, don't wait. Take advantage of the benefits that we see here in the studies that we've conducted, and we know from international experience even in different subjects, that retrofits are much more expensive than newly interconnecting technology, right? So when we can get in front of it and leverage the technology for new interconnections, it's in the end going to save stakeholders and ratepayers more money, as opposed to having to put urgent fixes on stability problems that could require retrofits down the road. So I'll leave you all with that, and yeah, thanks for following along with our project and our modeling and study work, and I think we have time for questions. So right on time, Julia.
Right. Yes, right on time. Thank you so much. A lot of questions. I don't think we'll get through all of them, but let's try. I think the first one is the most popular and people ask it a lot. Developers keep complaining that grid forming resources are expensive, and there is no incentive to install. Any ballpark estimate on incremental cost increase over grid following?
To take that one, I can take a first shot at it. This is a loaded question, as probably many of you on the call are aware. And I think maybe what I'll start with is just saying that the cost question is really out of scope for this particular effort. I think the main objectives of this effort was to talk about the technical aspects. Is this going to hurt the system? Is there something that we should be watching out for? The cost question, of course, is very important, and a lot of folks are very interested in that. I won't say much more than that, other than to say that the question says there's no incentive to install. I hope that this presentation shows that there is at least some incentive to install. I know we've seen extremely high benefits, both in terms of cost or mitigation of stability issues, unlocking of transfer capacity or of hosting capacity. And the third one, which is very important in some parts of the world, is damping effects on issues related to series capacitors and other things like that. So, the idea of whether this should be a market, whether this should be requirements and everything, I think that we all have strong opinions about that, but let's leave it for a different call.
The only other thing I would add, Andrew, is that and I think you hit on it, but when you look at the alternatives in some situations, right, the incentive is actually the ability to move a project forward, right? So I have extremely costly network upgrades, or I go with a relatively low cost solution option compared. So when you compare it to things like transmission infrastructure, synchronous condensers, these are orders of magnitude more expensive than enabling a control strategy inside of an inverter-based resource, right? And so again, like Andrew said it very well, we can argue about markets, incentives, or regulations, but at the end of the day, there is value in moving your project through the interconnection process and getting that thing online, avoiding the likelihood of curtailment, unlocking in another queue position for another resource, right? There's tremendous value actually in those things when you look at sort of that need for speed through the interconnection process. And I don't think those get enough attention, frankly. So I just want to highlight those.
Yeah, and maybe in the discussion of the cost, and I will not provide any ballpark, but I think when people think about costs, it makes sense to distinguish between like costs of like pure software and hardware versus costs of keeping reserves for provision of grid forming. So these are kind of two different issues and two different things to think about. So like maybe having grid forming capability, but not reserving any headroom for it is a lower hanging fruit there. Right, next question. How was load sharing ensured between grid following and grid forming IBRs? At what level of control the power sharing implemented for grid forming resources at device level or plant level?
I can briefly talk about that. It's on the plant level. So basically the droop settings on the plant level were adjusted to provide more or less the same kind of response.
And just a real quick one too, the load sharing, just like a grid following device, a grid forming device, you can give it a power order. They're dispatchable, so you can control that with your dispatch.
The next question, so there is a question about if we'll compile the questions after the session. Yes, we will, and we'll provide short answers and post them. So the next question is, to what extent should we expect these models to work completely disconnected from the grid? It means no voltage source, whether grid forming in parallel or a single grid forming.
Maybe just very briefly on the two microcosm test scenarios that we ran. The first one was so the NERC functional specification shows one GFM, basically of one type GFM. So the second part of the question is going to work if disconnected from the grid. And then the microcosm test system that we did was also showing that multiple GFM in parallel operation in an grid disconnected or IBR or 100% IBR system can also work. So in both, the answer to both is yes. It can work, operate either in parallel mode or in single mode of operate, single mode, one unit essentially.
Thank you, Farhad. The next question is, what will be the impact of including nonlinear load in the GFM functional test system?
I can take that one real quick. So there's nothing particularly special about the load in the simple microcosm system. It was a straightforward load. We don't expect the impact to be that interesting if you add a nonlinear load. In fact, in the ATC case, there are quite a bit more complex loads. So they have a mix of load types. It does add to the dynamics of the power system, but there's nothing particularly worrisome about that. I don't know if that answers the question or not, but
I think it does. I'll take one out of order. I think it's important one to the study. I remember some reports saying grid forming may not be stable when operating in strong grids. But why does case study 1 say that grid forming does no harm?
Maybe I can quickly answer it. I think it's a very, very good question, because this is something that we also had seen or had seen concern, and we've also seen very strong research that shows if a grid forming device is improperly tuned, it can become less stable in a grid form in a strong grid. And so I think that's one of the reasons for testing these things in a very strong system like this, larger than 50 SCR. And why Lukas identified specifically was looking for oscillations. So when he looked through all of the results and noticed that there was one case where the GFM took a little bit longer than we expected to damp in that very strong system. It was still really well damped. I think the answer is, like Ryan said, you have to test these things. If you're worried about it, you can put it in a system study. But there's nothing preventing a grid forming device from being stable in a strong system. You can improperly tune it and make it unstable. Okay, you can't indiscriminately choose parameters, for example. But there's nothing preventing a grid forming device from operating stably in a strong system.
Thanks. There's a question on slide 35. Why does battery 8 reactive power not stabilize properly and settle at such a low value compared to pre-fault operating conditions?
Lukas?
Not stabilized properly and settle at such a low value. The reactive power versus BESS 8 reactive power. Okay, yeah. So these BESSes were located at different parts of the system. So in the post-fault scenario, we would expect there to be different reactive loads, reactive demand, I guess, for the different resources throughout the system. So yeah, just depends on the post-fault topology of the network here. And it's a different between GFL and GFM here. It's a different, it's 125 megawatts more PV added in the case on the right. So the flow are going to be different as well.
Yeah, and just a little bit more just to sort of push back a little bit on the not stabilized properly. I think there's two things you might be looking at, and I realize it's Professor Vitale, so I want to be very careful and humble when I answer this question. But one thing is that the time scale of the simulation is only shown out to 2 seconds, so it's really hard to tell from this plot whether in the long term it does stabilize and settle down, and we can just tell you that it does. We can't show you on this plot. But the other thing that we can say here is that there is a little fuzz on the simulation there, which may be undesirable. But keep in mind that the goal for this particular case, Lukas was pushing the simulation to see how much more PV we could add. And so he was pushing it a little bit further. Probably if he would have gone a little bit further, we might have seen an instability in this one as well, just because we actually are right at the edge, the bleeding edge of that nose curve. So we have to be a little bit careful not to push it too hard. It is still limited.
And I think it, really wasn't actually highlighted in the discussion here, but one thing we did continue to touch on was there was many times like some type of thermal or voltage issue that would have to be addressed in addition to these stability problems, right? So it's not always the case that you're gonna just find yourself right at the edge of the instability condition. There are conditions where that N-1 instability is the limiting factor. But you have to sort of also take that into consideration. Am I within voltage limits post contingency? Do I have thermal overloads? Can I even pump this, 500 megawatts of power through this weak grid, just based on a normal PV curve type situation, right? So we were considering that, and we did run into that a few times throughout the study.
Great. So thanks so much. And we're at the top of the hour, so I will need to wrap it up. I would like to thank Ryan, Farhad, Andrew, and Lukas for the presentation today and for the fantastic study. As I mentioned earlier, an email will go out once the video file has been posted, and we will get answers to all these many questions that we didn't get to during the webinar. So guys, you will have to work a little bit more on this. We appreciate your engagement and look forward to seeing you again soon, perhaps during our February 18th webinar on analysis of IBR-driven oscillations in Australian grid. Further information on all of our webinars and meetings can be found on our website at www.esig.energy under events, and in our newsletters and information emails, and you are all invited to attend. Ryan, Farhad, Andrew, Lukas, thanks once again for this very timely, informative webinar, and thank you all for your interest and for so many questions. We look forward to seeing you again in the near future. Bye now.
Thanks, Julie.